This is molar mass of gases and gas density. So we're going to be using the ideal gas law to determine what a gas's molar mass is, as well as what is the density of a gas. So one of the trickiest things that I think I have seen, and the reason I think it's tricky is because we're so used to just using the periodic table, is what exactly is a molar mass? And remember, its definition is the grams of a substance in 1 mole of substance, or the ratio of grams to moles. Okay, so we just kind of get complacent in a sense and just go to the periodic table and look up what these values are. But sometimes solving for a molar mass is tricky if it's not a periodic table based thing. So if you have a gas's or any substance's grams or mass, and you also have the amount of moles that are in there, it's just simply the amount of grams divided by the amount of moles. And this actually goes for anything, not just gases. All right, so we want to make sure, even though this looks like units, in a sense, it's also an equation. We just need the grams, and we just need the moles, and that is molar mass, grams divided by moles. Here is the first gas molar mass problem. So the first thing is 0.650 grams of a gas. So I'm writing that down right now. The mass equals 0.650 grams. I have a volume here, 1.12 liters. That's great. Keep going and you see the temperature of the gas. Thankfully it's in Kelvin, so I don't have to do any temperature conversions. I'll write that down. And it looks like the pressure here of the gas looks like 1.14 atmospheres. So I'm going to write all of those things down. Remember that M, mass, is not the same as moles. If we know what the gas is, we can convert between the two using molar mass, which is tough in this case because we don't have the molar mass. But I can start here with the ideal gas law. So I will write that down. PV equals nRT. And I actually have all the things that I need to solve for N, the number of moles. So as I fill stuff in here, that is going to be the next task. The R value that I want to choose is the one that has ATMs in its units because my pressure right now is in atmospheres. So I'm going to pick 0.08821 liters atmospheres per mole Kelvin. And we'll just solve this once I have it all written out. So I can do 1.14 times 1.12. I'll divide it by 0.0821 and divide by 280. Also make sure I'm just checking my units to make sure everything cancels but moles. So this would make sense. It's unitless right now on the left side if I canceled everything. So if I got moles on the bottom and R. So anyway, the answer I get here for moles is 0.056 with a slight bit of rounding moles of whatever this gas is. Okay, well, the overall goal here is to figure out what is the molar mass of the gas, not to just get the moles. But I really don't have much further to go than where I am right now. Okay, so remember, molar mass equals grams per mole. And I actually have both of these quantities right now. I suppose I'll just write this in here so that way you can see it. Okay, I'll just plug in what I have for grams, which is 0.65 grams. And I will plug in what I know now is moles, 0.056 moles. And it's just 0.65 divided by 0.056. And I get a number of 11.7 grams per moles is the molar mass. Here is another molar mass of a gas problem. I'm going to let you try and solve this. So go ahead and pause the video now, and then when we come back, I will tell you what the answer is. So pause now. All right, we're back. So the answer that I get here is the molar mass is 38 grams per mole. Now, if we are trying to identify which of these four gases it is, well, it's not going to be NO because I get 30 grams per mole, 30.01. If I look up fluorine, fluorine is 19 in the periodic table, but there are two fluorines, so 2 times 19 is 38. That sure seems like that's going to be the answer. If you did 2 times chlorine's molar mass, because there's 2 chlorine atoms, you get 70.9, and the molar mass of hydrogen gas is 2.02. So if I knew the gas was one of these four candidates, fluorine is definitely going to be the answer for this unknown gas. So here's where things might start to get a little confusing. This is for gas density. And to take you way back into the beginning of the year, what does density mean? It's how much mass can you compact in an amount of volume. So it was simply the mass divided by the volume. We can rearrange the ideal gas law, PV equals nRT, to be the equation that you see here on the right. And you can solve for this quantity N over V, which is equal to the pressure divided by RT. And so you might look at that and think, well, that's the opposite of molar volume, and it is. Okay, so you might get these two things a little bit confused. So in this case, to get some gas's density, if I knew its pressure and temperature, and I knew what the gas was, I can then figure out what the gas density is going to be. I don't need to know the moles. I don't need to know the volume. I just need the ratio of moles to volume, and all I need for that is the gas's pressure and temperature. Once I have this ratio of moles to volume, so let's say it's going to be in moles per liter, I can then use the molar mass of that gas to figure out what is the density, and it would probably give me units of grams per liter, which we can convert, if we would like, to grams per milliliter. Hopefully this one will help it make sense a little bit. So I'm going to solve for this quantity, N over V, which equals P over RT. So I have a pressure of 2 atmospheres, and I am given a Kelvin temperature, 273.15, which is nice. I don't have to convert from Celsius to Kelvin. So I don't solve for N or V, just the ratio. I'll plug in 2 atmospheres here. The R value that I want is the one that has atmospheres in the units. Oops, not liter mole. Gotta cross that off here. Liter ATM, there we go, per mole Kelvin, 0.0821. And then temperature on the bottom here, 273.15 Kelvin. Okay, I can quickly solve for this, and this is going to give me that ratio of moles per liter, which is the opposite of the molar volume here. Okay, I'm checking to see if my units cancel. Notice I have liters per mole in the denominator, which means I got to flip those units, and the answer I'm going to get here is 0.089. I flip the units because they are in the denominator, so that is going to be moles per liter for units. Okay, so I'm almost there. I got one more step. I know that this gas is helium, so if I didn't know that, well, then I couldn't solve this problem from here on out. All right, so let me start again with the 0.089 moles per liter, which is that N over V quantity. And I will multiply it by helium's molar mass, which is 4 grams per mole, straight out of the periodic table. My units of moles will cancel. And this is now 4 times 0.089. And I get, let's see here, I get a final answer of 0.36. Look at my units now. They're in grams per liter. Now, often you're going to see the units in grams per liter for gases to make the numbers look nicer. You maybe were used to grams per milliliter. So if I instead wanted this in grams per milliliter, it's 0.00036. Those were the units that we used in the beginning of the year. But in the beginning of the year, we were dealing with solids and liquids, which have higher densities than gas. So, think about it. Water has a density of 1 gram per milliliter. Air, when you're walking through air every day, which you do, it doesn't feel like you're walking in a swimming pool. If air had a density close to that of water, that would not be very fun to walk through. It would also be somewhat difficult to breathe. So these are the density values. They are exactly the same, just different units. Usually, since gas densities are so low, they are often expressed in units like grams per liter, kilograms per meter cubed, something like that. But anyway, either one of these answers would suffice. All right, I suggest on this one, you pause this video and try it on your own. See if you can get the answer. And then when you come back, I will work through the solution for you. All right, this one says, at what temperature is the density of oxygen gas 0.5 gram per liter? So I'll write that down at 50 kilopascals, where we're going to have to go backwards. So I'm going to write down my 0.5 gram per liter and divide it by the molar mass of oxygen gas, O2 gas, which is 32. So 0.5 divided by 32 gives me this value of 0.016. If I check what my units are, this is going to be in moles per liter. And remember, moles per liter is the same as that quantity N over V, which equals P over RT. So I will just rewrite that down here, down below. Here we go. Let's see, N over V, okay, that's what I got. 0.016 equals, the pressure I will write in is 50 kilopascals here. The R value, I'm going to pick the R value that has kilopascals in for units. So 8.314 liter kilopascal per mole Kelvin. And the temperature is in the denominator, and that is what I am solving for. Now, some of you may have gotten to this point and had trouble solving for temperature. I'll just check our units here, and yep, it all checks out. Okay? And so one thing you want to remember here is if I were to bring this temperature over to the left side, it would be T times 0.016. So then I will divide both sides by 0.016. I can bring it into the denominator here. So to solve for temperature, it's 50 divided by 8.314, and then divide by 0.016. The temperature you get is in Kelvin, so I get 384.9. If I subtract 273.15, I would get the answer in Celsius. So either one of those two answers would be okay.